Hello fellow problem solvers, so there are we doing problem 4 from the 2022 IMO. A nice, here's the thing. Some people criticize this geometry. I'm okay with it. Not the greatest number 4 geometry of all time. I like different geometries, but it's a nice practice problem. Try it out for at least 10 minutes, ideally 30 to maybe an hour. Not more than 4.5 hours. You want to be able to solve this. If on the other hand you'd like to go along with us, draw the diagram. That's the first step here, so 5 minutes, take that. Now how are we going to draw? We have a pentagon. Oh my god, how do I draw this? With one condition, BC is DE. Okay, so if I'm drawing A, and I'm showing you how I'm drawing this because I have a point I want to make here. Say AB, and now I'll do a C, say here. My initial diagram isn't meant to be very good. Say D is far up over here. And D is over here and E is here. And this is our pentagon. And now, what is our, okay, there's a T inside such that TB is TD. Okay, what does that mean? Pause for two, I'm going to treat this as an introductory geometry problem, right? So pause for 5 to 10 minutes, think about what does this mean, okay? And it means that TB is equal to TD, means that T is on the side bisector of BD. Okay, that's where all these points are. And TC is equal to TE means it's on the side bisector of EC. So where these side bisectors intersect, that is where T is. And now, mind you, this condition and this one define T, unless there's an infinite amount of points where they intersect, but that would mean that BE is parallel to CE is parallel to BD, which is impossible because this is a convex pentagon, right? But outside of that, there's one point. They would have to be parallel, and also a lot of other things we need to hold true. So with that, we have T is defined by these two, and then we have an extra condition with T. Okay? And this condition is ABT. So actually no, it's ABT and TAE. Now here's my question for you. So far, we want to treat this point by point by point. What is easier? Is it easier for, how do we draw this? Pause for 2 minutes, think about how do we draw this? And the answer is, well, if we first draw ABCDE, we're going to have a problem. Where's how do we draw these points such that this angle condition is also true? So that's not the way. The way is to draw points BCDE first, and then after we drew those, the point is done. We can draw, instead of this being A, we're going to draw A here, right? And I want to make sure that these are different lines. And now it looks actually a lot more like my angle condition actually holds true. Okay, we're going to continue on with this messed up diagram. And let us see, what else do we have? So CD and CT. So CD is this. CT is this. Intersects what? Line AB intersects these. So line AB intersects over here. And it intersects over here at points P and Q, soon I'm going to give up PA, so such that this is true. And then we have a similar thing for DT, and CD intersects AE at a line. Okay, so now we know, why am I drawing a bad diagram before I draw a nice one? I now know, this angle should be kind of big, this angle, AE, I might want to draw, instead of, actually, when I'm drawing A, I might want to draw a bigger angle here so that they meet closer over here. Because this part is, pretty likely gonna be true. I know where to place A. A needs to be in the angle CDT, this angle over here once I extend it. That's where my A needs to be. So I'm giving myself some constraints. And the further out it is, the closer these other points will be. And then it will be easier for me to think about what is it that I need to do. Now, pause for 5, draw the diagram. here's my diagram. And now the diagram is drawn, the X's are here, the P, Q, R, S's are there, the T is here. And look at the diagram. It's much, much, much nicer than this thing we had here. This looks nice, sturdy, cool diagram. This one's like, oh. Okay? So, and we get to the nice and sturdy one from the diagram. Okay? Now, we have X. So many problem conditions. What do we do with them? How do we connect that this is equal to this is equal to this, and this is equal to this? Where do we even begin? Even before PQRS, how do we begin? And now is the time where I say we can do geometries in one of two ways. Forwards or backwards, okay? Let's go at it forwards a bit. And that's another thing that might be useful in general, is to take things a point after point after point at a time. So here, what do we have? We have, first of all, we first introduce point C, really. We don't need to listen to, like, A could be kind of an afterthought. I could say introduce T with these first two conditions, and then let's introduce A such that it's over here on this side and that these two angles are equal, right? It's important to note these little differences because it makes your drawing of the diagram much easier, and that helps you solve the problem much, much better. I mean, much, much quicker, much, much clearer. Like, the ideas are much easier to come by when you have this diagram as opposed to this one. Okay, like, what angles do I have here? So now let's look at this. Well, it's also good to, in geometry, keep in mind what is that we have. Okay, BC is DE, okay. I have TB is equal to what? TB is equal to TD. Okay, and TC is equal to TE. What does this give me? Pause for 2 minutes if you haven't figured it out, and the answer is, it gives me that these two triangles are in fact congruent, like the triangle TBC is congruent to the triangle TDE. Okay, and this congruency is now going to give me some angles I did not have before. So, for example, it's going to give me this angle over here, let's call this Z, is equal to, so TCB. So I get TCB is TED. TED. This whole angle here is Z. And if I call this angle Y, then this whole angle over here is also Y. Nice. No, nice things that we're figuring out as we go along with our problem. Woohoo. So now, what else do we have from this? Okay? Do we have anything more? We're doing these intersections. This is X plus Y. Okay, so this is 180 minus X minus Y. Let's call this angle here that they share also T. So instead of writing 180 minus something, I like to write, T plus Z. Sometimes that can mess with you if you don't know, if you forget that the sum of what is 180. So Y plus Z plus T is 180. And now this is 180. So we have, this is Z. Do we have these angles at all? Well, we have that TC is TE also gives us that this angle over here is equal to this one over here. Okay, and we also have that, what's it called? This angle is equal to this one. Do these configurations give us anything? Well, the sum of these two angles and the sum of these two angles is identical, right? They share T plus this little side, plus these two, is 180. And then T plus this side, plus these two angles, is 180. So these are in fact the same angles. Pause for 2 minutes if you didn't see that. And so, which means in fact that T, this intersection over here, CB are concyclic. Might be useful, might not be useful, right? But just something good, keep in mind. It might be totally useless. Why did I even look at this? But maybe it's not. Who knows? So we have, okay, that these are concyclic. We might use that in the future some way, somehow. Maybe not. Maybe I'm foreshadowing. Maybe I'm not. What else do we have? Okay, so this is z. This is t plus z. So that will give me that this angle over here. This is t. And now here I invite you, wait, this does not really make a lot of sense. If this is t, this is z. How is this angle over here equals t plus z? Well, maybe here is a good place for you to pause for 5-10 minutes and try to push the problem further. And here is the next step. And what we actually didn't see beforehand was I needed to do a minus x here as well, because t plus y plus z is 180. So I have an extra x here. I need to subtract that. And now, what is this leaving me with? That means that this angle over here, z plus this, needs to be z plus t minus x. So this one is t minus x. And similarly, in a similar fashion, I should get, okay, this is BQC. What is the analogous one? The analogous one is DSE. Here I have t plus y minus x. So I should get what? Y, t minus x as well. And now this is sort of this is cyclic, like SQ and say these 2 points over here give us a cyclic quad, but we need PRQS to give us that cyclic quad. We need these to be cyclic. Okay, so how are we going to proceed with this? Well, now we can go backwards. I invite you to pause for 5 minutes and think about the problem backwards a little bit. Okay, so what do we have backwards? Well, we'd have, how do we even approach this is the big question. How do I even connect the P with the A, the Q, S, like all of these, right? That is our big question over here. And now, okay, so we need to do some thinking. Now, let's see maybe. Well, these two are, what's it called, concyclic. So if this whole thing was cyclic, then this angle over here would be equal to, let's say, this angle here was phi, then this one would be phi, but then because the cyclic ones, this one would be phi. So it's enough to prove that this is parallel to this. Now, do we want to put these 2 points in here? Does that make the problem easier is the question. Does it make it easier for us to look at the problem, not in terms of these S and Q, but in terms of these 2 points, intersections of CT with AE and DT with AB. Like, they're roughly similar in nature, just there's this difference. We can also, like one follows from the other. So now, what are we going to do? Well, okay, let's see. Do we have anything else from the fact these are concyclic? Well, we have this angle over here. What's it called? This angle is equal to this angle. And now look at what we have. We have an x, we have this angle. So we have, well, let's name this angle somehow. Let's call it, let's call it, instead of this one, which we called phi, looking at the problem backwards, let's call this one here phi. Okay, so now we have phi x, and this is 180. Say this is beta and beta. I'm just naming everything I can. But I'm not really doing that. I'm just like trying to get a sense of what's happening. I have beta plus phi plus x is 180 as well. Good to keep track of that as well. And now, okay, what does this give me? Pause for 5 minutes, push the problem further. What do we have? Well, now we have angle, similarity. Oh, wait a second, this similarity, and we have these interesting, we have these sides that we've used in this congruency from before. So we might want to pay attention to that. Now, what does that give us? Well, it gives us that xtb is similar to yte. Now we've labeled these points accordingly. Okay, so now let's see, does this give us anything else? We have a t, a beta, these angles, like, do we have a line over here? We have a line over here. So this is equal to this. We don't really have anything just yet, just now. I feel like we're close, but we're not there yet. The sum of these two angles over here is what we need. It feels like we're getting closer to the problem, but we're not there yet. So let us continue that. Maybe there's a way that we can actually figure out what beta and phi are in terms of x, y, z, t. Maybe, but maybe not. Like right now, I don't see the need to go down that route. So let us continue on with this. xtb, yte. So what does the similarity give us? And I want to see what the similarity gives us. Why? Well, I want to see if there's anything I can do when I look at d instead. Like td instead of bt. Maybe it's something, maybe there's nothing. There's many different things we could look at here. So let us see what the similarity gives us. And also, important thing, write stuff down. Things you figured out, write them down. So we have xt over yt is equal to bt over et is equal to xb over ye. Okay, so xb or ye is equal to this over this, right? And it's also equal to this over here over this over here. Well, now the thing is, okay, can we transport anything anywhere? Let's think further. So if these were in fact parallel, we'd have this angle is equal to this one, but it would also mean that this angle over here is equal to this angle. Is there a way we can connect that? Can we connect these angles in some way, shape, or form? So what is this angle? We have this angle over here that we've been looking at, plus this one needs to equal this one somehow. Like, what would that mean? We'd have these two are similar. We would have, here's what we would have. We'd need to have opposite, like we need to have that xt over yt is equal to this over, like we need to have the opposite, like the similarity here between these two triangles, right? That would give us two angles. And here's the thing, we have one angle, and if we had one, we'd have the other. We'd get two at the same time somehow. And can we get that through the angles? Well, not really, not now, because we don't know what this angle is. We don't have it quite yet. So if we can't get the angles from other angles, let's try to think about, can we get it from the sides? And from the sides, it would mean that getting it this over this would need to be equal to this over this, right? This opposite this angle over this opposite this angle would be this over this. So let's write, so what do we need? We need to have so many markers. We need less markers in our hands. Need tx. We don't have this yet, and that's why I'm using green, which is not very legible, but still I'm trying to say this is what we need, and I don't want to confuse it with what we already have. Tx over ty, tx divided by ty. What is opposite tx? It's this angle over here, and that is the same angle opposite this. It's td over tc. That is what we need. So now let's see what we have. We have tx over ty, and we have its bt over et. Well, bt over et is in fact, bt is equal to what? bt is equal to dt. And then this et is equal to ct. And now this over this is equal to this over this. Combine that with the fact that we have the shared angle here. And then now, from there we get that combining this and the fact that the angle xty is equal to the angle dtc. dtc. From here we get that the triangles xty is similar to the triangle dtc. And from there we get that this angle over here is equal to this angle right here. And now that implies that CD is parallel to XY, CD is parallel to XY, and CD parallel to XY implies PR is parallel to XY. And now this implies, PR is parallel to XY. And so call this angle here alpha. That means that this angle here is alpha because these two are parallel. And from this here concyclic quad, we have this angle here is alpha. And now the angle QSR and QPR are the same. And so these points lie in a circle. I don't know of a, like, this is for me a problem that is pretty, linear in your thinking. There's not a lot of things that are happening here, right? It's not, there's a lot of things that are happening here. But the reasoning seems to be unidirectional. The big idea was these points X and Y, which makes sense to look at them a little bit once you get these two angles are identical. And then you see, like, then maybe your whole focus changes. You need some way shifts in some way to take the sides, the side lengths and everything. You need to take it from there to some angles. And that's where similarity becomes like a big idea. So that finishes up problem number 4. Please let me know in the comments below if you have a different way of thinking about this, a different way you've come to a solution. For me, this was one-to-one how I've come about it. I've thought of this point over here, introduced it. Didn't see really any other way I could use this fact about T. Once I had A, like this was my thing for A. There wasn't anything else really. Like, what is this angle condition also? Like, maybe something interesting to think about. This angle condition X and X. It is, in fact, I think, if I'm not mistaken, this is X. If this is if this is X, and if this is X1 and X2, this is minus X1, minus X1, minus X2. So the fact that these two are equal is that these two angles are equal. So the fact that these two angles are equal is the same as the condition that ABT and AET are the same. So this condition is the same as this one. This condition is much closer to the problem. And also, A is then an intersection of diagonals. A is less important. Like, A isn't that important to begin with, but that way I can forget about A, right? And I can just focus on this condition over here with these angles. And now, okay, I have these two being parallel. Like, that's the other thing I would need to prove in a different way. I can connect somehow these sides, right? I have these sides. And this is a general thing in problems. If you have like two sides being equal, like sometimes there's a similarity with this side and you want to transport it to the other side. And that's what we're doing here. That is that general, really loosely speaking, a general heuristic thinking for similarity problems. And this finishes up our lovely problem number 4. You know, I told you, it's a good practice problem. The big part, I think the big challenge here was, how do you not get lost in all of these signs and everything? Look at how many things we have on the board. Just look at this. What is happening here? That's the big challenge with this problem. I hope you enjoyed it, and as always, thanks for problem solving.